Brett Jareer, who used to run the DARPA Defense Sciences Office. George Post, who was one of our big speakers and a luminary, and they all want to know what you can do. So let us have it. Good, great.
So shall we start?
Yeah, go ahead.
Go ahead.
No,
Are you on?
Okay, so first let me introduce myself. My name is Jie Wang. I was a postdoc working with Professor Jie for the last 3.5 years. Recently, I was promoted to a research assistant professor. So today, I'm very glad and honored to present our work in the past 3.5 years. So the topic of today's talk is Sparse screening for big biomedical data. Actually, when I prepared this talk, it really took me a long time to decide if I should include this keyword or not, because our method is not limited to biomedical data. Our method is actually very general. We do not make any special assumptions on the data. So essentially, it can be applied to any type of data. Okay, so right now there are many ongoing projects carried out by our group. Here is a list. We have Drosophila umbrogenesis, Alzheimer's disease, major depression disorder, and imaging genetics. A common feature of all of those projects is that they all involve huge scale data. So in many biomedical applications, the data is quite wide and fat matrix, which means that the number of features can be much larger than the number of samples. So for example, for the adenine data and the GWAS data, many data set has a few hundreds or thousands of patients, but it may have millions or tens of millions of covariants. So the data is a pretty wide matrix. In many other applications, such as recommender systems or image classification, we have millions of samples, but the feature dimension is not that high. So for those kind of applications, the data is tall matrices. Okay, so from many studies, many real-world applications, we have a common observation, which is for the data with millions of variables or complicated structures, it can actually be well interpreted by a very small subset of the features.
Yeah, he's standing. I think you can sit down.
Yeah.
Yeah, right. He's got to get away from the pizza just in case you get on it.
Okay, so there are actually many algorithms proposed in the past decades to select important features. One of the most popular and powerful class of methods is the so-called sparse feature learning models. I will explain a bit, in detail what's the meaning of sparse feature learning models. So for another type of applications, like we mentioned before, the data matrix is very tall, which means the number of samples is much larger than the number of features. So for those kind of applications, studies have shown that we can frequently find a small subset of the most representative data instances. This subset of representative data instances can be very helpful for us to understand the underlying structure of the data. So some well-known methods for those kind of applications is support vector machine and k-means clustering. Okay. So there are many, like I mentioned before, there are many algorithms proposed to select the most important features or the most representative data instance. Many algorithms are the so-called heuristic-based data reduction method. For example, sure screening, random projection, something like that. Those methods actually works pretty well in real applications. This one is proposed by a leading figure, his name is Jianqing Fan, who is a professor in Princeton University. This method is actually very popular. But for those kind of method, the resulting model is actually an approximation of the true model. However, the authors claim that their method will sometimes result in better results with better statistical properties for some specific scenarios. And also, there are many existing works analyze the quality of the approximate solution. So for the past 3.5 years, we have devoted a lot of research efforts to a topic named Sparse screening. This is actually a new framework for exact data reduction. I have to emphasize that this method is exact. So what does it mean? Exact means the model learned from the reduced data is guaranteed to be identical to the model learned from the full dataset. This is probably one of the most appealing features of our method. So in this talk, I will focus on two models. The first one is Lasso for wide data, which is a feature reduction method. The second one is support vector machine for tall data, which is a sample reduction method. I have to mention that the framework of our method is actually pretty flexible. It can be extended to much complicated sparse models, and I will mention one of them in this talk. Okay, so before we introduce what is Lasso, let's give a brief review of linear regression. So the linear regression, although pretty simple, linear regression model is probably still one of the most popular methods in many applications. So for linear regression model, we usually assume that the outcome, y, is linear regarding to the regarding to the variable, regarding to the covariance. And epsilon is noise. We usually assume this noise term obeys the normal distribution. So the goal for linear regression model is how can we estimate the coefficients? How can we estimate the coefficient vector? So rich regression is actually a widely used technique to estimate the coefficient. For example, A is our data matrix, and X is a coefficient matrix, and this Z is actually it represents the noise. So the objective function of rich regression consists of two parts. The first part is a loss function, which measures the fitness of the model regarding to the observed data. And the second one is a regularizer. This is actually usually limit the complexity of the model, because we know that complex models is usually prone to overfitting. So in case you don't know what's the meaning of overfitting, overfitting is so intuitively overfitting implies poor generalization performance. So more specifically, overfitting means that you may have very small training error, which means your model fits the observed data pretty well. However, it may give you very poor generalization performance, which means this model may result in huge errors on the testing data, right? Okay, so Lasso is actually another method to estimate the coefficient vector. So the only difference between Lasso and the rich regression is the regularizer. You see, we have the same loss function, we also make use of the least square loss. However, we use the L1 norm as a regularizer. So the major property of this L1 norm is that it will result in many zero components in the solution vectors. Right? So according to matrix and vector multiplication, let's assume that this component of the coefficient vector is 0. So what does this mean? It means the corresponding feature has nothing to do with the outcome. Right? So in this case, even if we remove this feature from the data set, we will essentially get the same model, right, as a final stage. Okay, so essentially, Lasso can achieve the goals such that Lasso can achieve the goals of regression and the feature selection simultaneously. So this is why Lasso is so popular in the last 10 years. It's widely used for feature selection. Okay, so probably Lasso is one of the most popular sparse learning models. So right now, let's give a bit of more explanation of what sparse means. Sparse actually, it means many zeros. So intuitively, sparse means many zeros. There are many zero components in the solution vector. Or sometimes the coefficient may not be a vector. It can be a matrix. So sparse means a lot of zero components. Right? So sparsity has actually become an important modeling tool in many applications, including genomics, genetics, signal and audio processing, image processing, neuroscience, machine learning, statistics, many applications. So this is, let's just introduce a bit of background of Lasso. Lasso is first proposed by this guy, Robert Tibshwani. This is a professor working at Stanford. He actually won the COPS prize, which is kind of like the Nobel Prize in statistics. This guy has been a member of American Academy of Science maybe 2 years ago. Yeah, this paper Lasso was first proposed in 1994, and this paper is actually published in 1996. However, in the first 10 or 15 years after the publication of this paper, actually there are very few of people know this method. The reason is probably because it's probably due to this regularizer, because this regularizer is non-differentiable, right? Many traditional optimization algorithms are not applicable to solve this kind of problem. So in the first 10 or 15 years after the publication of this paper, this model is not very practical because we do not have efficient solvers to solve the Lasso problem. Usually, we can only solve the Lasso problem on a moderate data set with maybe a few hundred, thousand of features, and even for thousands of features, it may need days of computations. So this is probably the most important reason that limits the application of Lasso in the first 10 years after its publication. But right now, you can see that this paper is cited by 14,000. So if you are a researcher working in machine learning and statistics, then probably Lasso, probably one of the most well-known models. Okay, so why Lasso becomes so popular in nowadays? So the reason is maybe back to 10 years ago, we have a breakthrough in the optimization technique. We have developed many efficient algorithms to solve the non-smooth, non-differentiable objective functions. So some of the state-of-the-art algorithm include coordinate descent, subgradient descent, augmented Lagrangian method, gradient descent, accelerated gradient descent. Lot of them actually. And our group has contributed significantly in this area. We have proposed many efficient algorithms to solve the Lasso type algorithms. And our group also developed a package named SLAP. SLAP implements many state-of-the-art algorithms for the Lasso type algorithms. And right now we have 4,500 users from 25 countries. And this package receives about 230 citations until now.
And how long has that been going?
This package is developed, I think, around 2010. 2010, yeah. Okay, and this package is actually publicly available. So, but to be honestly, I have to admit that this method is not state-of-the-art anymore. So right now we have a much more efficient solvers proposed by a guy from Austin, from the University of Texas at Austin. We have developed a much more efficient solvers. But for monolith dataset, it still works. Okay. So yeah. So after this talk, if you are interested in this topic, then we can talk about this. Okay. So however, we know that the scale of the data increases explosively in the past few years, right? And it's still keep growing very quickly. So for those traditional algorithms, what if the dataset is extremely huge? For example, a dataset with millions or billions of variables. And even worse, in real applications, we usually need to run the solver many times for model selection and for parameter tuning, right? So this imposes even greater challenge to all of the existing algorithms, right? So in the past few years, we're actually trying to answer two questions. The first one is, can we make any existing Lasso solver much more efficient? This is the first question, can we? And the second question is, if yes, how? So we spent last 3.5 years to answer those two questions. And it turned out that we get pretty good result. And our method works very well in real applications. Okay, so now let's go to today's topic, our work, the sparse screening. So let's see, we have original data, which may have 1 million variables, right? And based on the sparsity assumption, we know that a very large portion of the features has nothing to do with the outcome, right? So let's just think, if we can pre-identify the features that are irrelevant to the output, then we can remove those, we can throw away those features, right? And we can obtain a significantly reduced data set. Then we may be able to apply any solver on this reduced data set, and we can get essentially the same model, right? So this is a high-level illustration of our idea. So for the first one, this is the traditional method. We just apply the solver to the full dataset without screening, and we can get a solution. And the alternative, we provide an alternative option. That is, we first apply some simple rules to pre-identify the features that are guaranteed to be relevant to the outcome. Then we can remove all of those features We can throw them away, right? And then we can get a reduced data set. But finally, we apply any solvers. We apply your favorite solver to solve the model on this reduced data set. And one of the most appealing features is we finally arrive at the same solution. And actually, our work turned out to work pretty good in many real applications. And maybe the result is too good to be true. So it's not very smooth for the publication of our method. We published a conference version in 2013. And our journal version is finally online this week. So okay, so let's
Just in time for this presentation.
yeah, yeah, just in time. Yeah.
So good. You're going to tell us about the screen.
Yeah. All right. So like I said, so today I will just talk about our screening method for some simple sparse learning models. So this is a standard Lasso. This is a least square loss. This is a regularizer. The y is the outcome, x is the data matrices, and beta is what we need to estimate. Right? So this is a figure illustrate. Actually, I have already mentioned before, because we assume Lasso is nothing more than a linear regression model. Right? The only difference is we induce some sparsity in the model. Right? So let's say this is outcome, and this is features, and this is the true model. And we know that because due to the L1 regularizer, we will eventually have many zeros in the coefficient vector. And we know that a zero component implies the corresponding features has nothing to do with the outcome, and which can be thrown away from the optimization. Right? So it turns out the idea of our axiom actually originates from the dual formulation of Lasso. The dual formulation of Lasso is actually a projection problem. This is a dual optimum. It's actually the projection of y over lambda onto the dual feasible set. The dual feasible set is a polytope. And according to this geometric intuition and the optimality condition, so don't be afraid of this term. The KD condition is nothing more than the first order optimal condition. Right? You just set the gradient equal to 0 or something like that. So combining the geometric intuition we mentioned before as a KD condition, we can finally arrive at this simple rule. This is linear, right? So it's actually very simple to solve this optimization problem. And if the maximum value is strictly less than 1, then we can conclude that the corresponding component of the solution has to be 0. And then you can remove the ith feature from the data matrix. So I will skip those math techniques. Actually, they are pretty sophisticated. So the main idea of our axiom is to make use of the non-expansiveness of the dual optimal solution. So finally, the framework of our method can be divided into 3 steps. The first step is we estimate the dual variable. We estimate if the optimal solution of the dual problem. It turns out that we can use a ball, we can use a very small ball to bound the dual optimum. And the second step is to solve this simple optimization problem, right? Because the objective function is linear, and the constraint set is a ball. So it's actually very easy to solve this problem. And finally, it's just determine if SI is strictly less than 1 or not, right? If SI is strictly less than 1, then we can conclude that the corresponding component in the coefficient vector must be 0, and the corresponding features can be removed from the optimization. Okay, so now let's see some results.
Sorry, question here. Can you go to the slide?
Yeah.
So what's the intuition behind this maximum of the Q times X being less than 1?
This one. For this one, this is derived from the KKT condition, the first order optimal conditions. Yeah, from here.
So can you like try to say in terms of initial data, what does it mean? What does it supposed to mean? What's the intuition behind this?
Let's see. This actually this is a good question, but it may not be that easy to answer because it involves actually quite a lot of math. So this is a first order optimal condition, and based on this condition, we can derive this equation. If this inner product is 1 or minus 1, then the corresponding components must be a non-zero. Otherwise, if it's in this closed interval, then it must be 0. So according to these two rules, we can conclude that if the absolute value of this inner product is strictly less than 1, then the corresponding component must be 0. So this is actually algebra. Yeah, this is actually algebra.
One more question.
Mm-hmm.
Can you go to the next slide?
Yeah.
Next.
Mm-hmm.
Can you do this for multiple lambda simultaneously, or you have to fix lambda and just run your calculation? If I choose another lambda, you have to run again, or you can solve it simultaneously?
We have two modes. The first mode is you can fix one lambda and run your model along a sequence of different values of lambda. This is the first mode. A second mode actually performs much better than this one. That is, if you have a given sequence of lambdas, then each time you fix your lambda value and you solve the model, you run these rules on the next value of lambda. After you run this model, then you go to the next one, and you repeat this process until you have solved the models for all of the parameter values.
So the second mode is much faster than
Yes. Much faster actually.
So you can use the information from previous lambda.
Yes, exactly. This is actually a very good question, and this technique is very well known in the optimization community. It's called warm start. So if you want to learn more, then maybe we can.
So will the same technique work? Let's say if you have the sparse input, if your input matrix is sparse as well. Will this work?
Yes, because we do not assume any special structure on your data. Your data can be dense. It can also be sparse. Yeah. Okay, so let's see some experiment results. So this data set is very well known in image classification. This is a data set of handwritten digits. 1, 2, 3, 4, handwritten digits. And our goal is to fit the Lasso model on the dataset. The dataset is actually I forgot to mention the dimension of the data matrix. The data matrix actually has 50,000 features, and that yes, 50,000 features. And the sample is about a bit more than 700. Yeah. So this shows the running time. The first column shows the running time of the solver without screening to solve the problem 100 times. So essentially, the solver needs about more than 40 minutes to fit the model 100 times. And this is our method. Actually, this is a preliminary version of our method. It needs about 5 minutes, 5.5 minutes, and this is the improved version of our method. It only needs a bit more than 10 seconds. So compared to the solver without screening, we can see that this trick, you can see this is a trick. This trick actually earns you 230 times speed up. Right?
So do you have any results compared to like traditional methods
have like heuristic methods, how do they perform?
Actually, this one is a heuristic method. That's all.
Feature reduction.
No, this one is strong rule. This method is proposed by Robert Tibshani. Yeah. Actually, they have spent a long time to find out why their method is heuristic based. They actually spent a long time to prove their method is accurate, because in real applications, the method is almost correct. The method will give you, most of the times, the method will give you the correct answer. However, in their paper, they do mention a counterexample. The method can make mistakes. So that's why they call their method a heuristic method. And they spend a very long time to prove their, to fix the method. So this is one of the reasons. After we published our work, Tibshani actually emailed our group, and he is very glad to see that we have solved this problem. We have proposed exact screening method, and the performance is comparable to strong rule.
So is this real data or
Real data, real data.
What do you have with 50,000?
Images. This is handwritten digits.
Like CT scans.
And these are 3D or
2D.
2D?
2D. Yeah.
There's 50,000 parameters in them?
50,000 images. This is kind of,
That's observations and that's samples.
yeah.
He's asking how wide is the matrix?
For each image, we actually we vectorize those matrices. This is kind of like a face recognition application. So in this application, you reverse sample and features.
So if you take random number distributions and make 50,000 of them and try.
Yeah, yeah.
What do you come up with a
We
significant?
have 40-fold speed up for synthetic data set.
I'm talking about if you just take random number distributions and you make 50,000 of them, will you get something that comes up looking significant? That's an awful lot of parameters that you're starting with.
He's dealing with your overfitting question.
So it's like, would be a multiple testing problem in standard statistics.
Yeah. I understand your question. So I think I may need to clarify that we didn't propose any new model. This model is still Lasso. Our work is to speed up the computation of Lasso on the extremely huge data set.
Basic premise underneath that.
Yeah, I think it's important to disclose what the data and what the features are in the data, and ultimately what,
You've got an awful lot of
in
combinations.
the ground truth of the data, what is the result, not just the speed up, because it could be speed up against this random number bot.
That's totally.
Give you a bunch of overfitted random numbers.
I think that's totally determined by. Yeah, that's a very good question in real applications, actually. But this is actually totally determined by the property of Lasso.
Yeah, I'm just like how many parameters can you push this to before you just start randomly, you find some that work.
Well,
Are you going to show us examples?
that's equivalent to taking any model and that big number data set that you're saying, like linear regression or something. And
Agreed. I just
well,
Okay, so I think you understand. So what
What's the time?
Yeah. So in this talk, I just mainly focus on the speed up of this of our method. So for the real applications, actually, we do have some papers, but maybe we can I can present in my next talk. So today, let's just focus on the speed up because this is our major contribution. Okay, so this is a rejection ratio. It actually reflects that our method can correctly identify almost all of the zero components. The ratio is approximate to 100%. So this is experiments adding data. The size of the data matrix is 747 and it has about 500,000 variables. And the response is the volume of the brain region. And without screening, the solver actually needs more than 10 hours to fit the model. But with the tricks, with our screening method, the time is reduced to about 3 minutes. Right? For these experiments, we actually evaluate our method on even larger data matrices. The x-axis represents the number of features. The unit is million. And we can see that if the number of samples is roughly the same, then the speed up gained by our method will increase as the feature dimension increases.
So what are these features?
These features are they're actually SNP data. Yeah, the SNP data. Yeah. So this is a pretty new book published this May, written by 3 leading researchers in our field: Trevor Hasty, Robert Tibshirley, and Martin Wainwright. This guy is the guy who developed Lasso. This one, he's also very famous, working in statistics. And everyone in statistics believes he will eventually be a member of American Academy of Science. In their book, they spend a whole section to introduce our method. This is the preliminary version of our method, and they give very high compliments of our method. In fact, our method is one of the best methods in screening. He said the method is actually dominant with the earlier 6 rules.
Yeah, no, it's really fantastic.
Yeah. Yeah, maybe our paper is accepted by the Journal of Machine Learning Research and published this week, probably due to the publication of this book. Yeah. So, like I mentioned, our method is the framework of our method is pretty flexible. It can be extended to pretty complex models. For example, the tree lasso. In the tree lasso model, the regularizer, we assume that there's a tree structure in the features. And this one is actually very complicated to solve. But we finally show that we can extend our method to these complicated problems. Oops. And also, I created a website to release our code and some resource. You can take a look. If you are interested, you can take a look at this website, download the code, and play around. We may have we may have a Python version and R version in the next few months. Okay, so we have talked about the Y data. Now, next, let's talk about the tau data. So, like I mentioned, SVM, the support vector machine, is a widely used technique to select the most representative data instance. Support vector machine is a maximum margin classifier. It actually will give you a hyperplan. This hyperplan will separate the positive samples and the negative samples. And it tries to maximize the margin of this, actually represented by this yellow region. One of the most appealing features of SVM is that SVM is determined by the so-called support vectors. And compared to the whole dataset, the number of support vectors might be very small. For example, in this tau example, only 3 data instances are the support vectors. So our question is, can we make use of this observation? Because SVM can be determined completely by the so-called support vectors. This implies that the non-support vectors are irrelevant to this classifier. Right? So our question is, can we make use of this observation? So the screening, the high-level idea of screening for SVM is, this is the original problem, and we first apply our testing rule to identify if a data instance is a support vector or not. If the vector is if we can guarantee that the vector, the data instance, is a non-support vector, then we can remove those non-support vectors from the optimization. And then we can apply any package, any existing solvers to solve the support vector machine problem on this reduced data set. And the framework is almost the same with that of the Lasso. So first, we estimate the due optimal solution. And second, we solve two simple optimization problems. Finally, we just tell if SI is strictly larger than 1 or TI is strictly less than 1. And then we can identify a large portion of the non-support vectors. So this is an example on 3 synthetic data. We can see this figure represents the rejection ratio. The ratio between the number of identified non-support vectors and the non-support vector in the ground truth. So this figure shows that our method can correctly identify almost all of the non-support vectors, even for data sets that largely overlaps.
So do you have various kinds of noise that you put in this? I mean, do you look at the effect of noise?
For this example, yes, we add a noise to the data instance. Yeah. Yeah. And this is experiments on several real data sets. This shows the speed up gained by our method. And we can see that combining with our exome, it can actually give you up to 80 times speed up. This is another widely used model, which we call the LAD. It's pretty similar to SVM, so I will just skip this one. And for this one, the performance is even better. It's more than it can give you more than 100 times speed up. So here is a summary. So our work on Sparse screening in the past 3 years can be summarized as we have developed a suite of novel techniques. The first type is for feature screening, and the second type is for sample screening. And the most appealing feature of our technique is that the model based on the reduced data is identical to the one constructed from the full data. And experiments show that our method works pretty well in real applications. And here is some summarize a bit of our future work. Actually, we still have a lot of work to do. For example, we may need to develop the screening method for more complicated sparse models, like the the graph Lasso, something like that, and for non-convex sparse models. And actually, in recent years, many studies on real applications imply that non-convex sparse models usually perform better than convex sparse models. So this is one of our future direction. Okay, I think that's it. Thank you for your attention. So, do you have any questions?
Should be some. Great. Thank you very much. How about some questions? We got some time for a good discussion here, which isn't always the case. There should be some questions. We've had some already. I guess mine, to begin with, is a little bit more understanding. This is related, I think, to Jeff's questions in general. I mean, what kind of, more about what kind of data, sets are you working on now, and what kind of data do you think this kind of are heterogeneous, like maybe like in the ADNI project with the SNPs and the cognitive models and the images. You know, I mean, what kind of where does this kind of technique shine in the context of computational biology and bioinformatics? You know, in biomedical and clinical informatics. I mean, the stuff we care about.
Yeah. So, like I said at the beginning, our method didn't assume any specific requirement on the data. So basically, it can be applied to any type of data. But speaking of the real applications, actually our method performs the best when the number of samples is much less than the number of features. The reason is because, for example, for Lasso, the reason is because theoretical properties of Lasso guarantee that the number of features selected by Lasso is upper bounded by the number of samples. So if the number of features is much larger than the number of samples, this implies that the solution will be very sparse. And then our method works the best. But if your solution is not sparse, if the ground truth is not sparse, then our method may not be that useful.
Do you have any specific examples of problems that you've tried to solve or tried?
Yeah, for example, right now we have many data. For example, the MNIST data, the GWAS data. For those kind of data, the number of patients is usually not that large. We usually have a few hundreds or thousands of patients. But the features, for example, the GWAS data, we may have millions of covariants.
Right.
So
So
they combine MRI images and GWAS. Say also.
For MRI images, we usually use the volume of the brain region as a response. Yeah.
so do you train, you know, for the MRI case, do you train against three-dimensional sets of imagery and then turn a learner across the larger set of brain images? I mean, it would be maybe the hippocampus or the prefrontal cortex, some kind of, you know, some ventricle. I mean, Jerry's the expert on that, but you know, you know, what kind of intervention you do ahead of time to kind of guide your machine learner against the three-dimensional brain imagery?
So right now I think the data I have is processed data. I have directly the volume of the brain regions, and I know that this is corresponding to which region. For in our real experiments.
So you have a table of the volumes of the various brain images
Yes.
that are supplied by image processors.
Yes,
that
yes.
Do the machine learning.
And
so you're really you're learning on you're machine learning against numbers. Yeah. Boy, I don't know. That's I can understand that, but okay. So you have in the ADNI case, you have GWAS, and you know there was a number of different GWAS studies that were brought together. So
Yes.
you know, but there were relatively few SNPs within the GWAS.
Yes,
that
yes.
ultimately were reported against maybe a nominal population
Yeah.
in aggregate of about 100,000 patients, something on that order. You have the cognitive tests, you know, mild cognition, or, you know, people are severely impaired. You know, you have age. I mean, I think you have gender, maybe ethnicity. Then, you know, so the images, the cognitive tests, and the SNPs. So this is related to Dr. Roman's question. Then how do you bring all that together and process that together? What kind of questions do you answer? And I mean, is this data set an appropriate one to think about in terms of the sparse learner? It might be.
Yeah. You sort of have to make assumptions, right?
Yes.
Include everything.
So first, we first select the volume of the regions which is known most related to Alzheimer's disease. For example, the hippocampus, and we use that as a response vector. And then we just directly put the GWAS data. We put them together, and on this data matrix we train the model to see if the Lasso can correctly identify the most relevant SNPs. So now our results show that Lasso can Of course, we need to combine some other techniques like stability selection. Combining with those kind of techniques, experiments show that Lasso can correctly identify the SNPs corresponding to the genes which are known to be most relevant to Alzheimer's disease. For example, the ApoE, the gene ApoE. Yeah, Lasso can correctly identify.
Such genes you have besides ApoE4.
Not many.
Not many.
That's the problem.
Mm-hmm.
Other questions, comments?
Yeah, quick question. So you said that's like the main property of the method why you were working on that is that can do regression and the feature selection at the same time, right? So and it was slow, and then you like spent a lot of years to trying to speed it up.
Mm-hmm.
Did you try to compare that performance to, for example, if I take the same data and I throw like in a distributed random forest that can be like parallelized very easily and train like trees on a multiple, computers on a multiple nodes, and then it also provides the feature importances that allows you to do a feature selection.
Yes.
So, okay, did you like compare if it's worth it to do speed ups of the Lasso versus like just using the redistributed random forest on the data and getting the fixed feature selection as well?
I think the reason for why we do this kind of work is right now Lasso is still one of the most popular methods in feature selection because it's simple. And so if you have an extremely large data set, then sometimes you might not be able to use some fancy models, like you said, the random forest. If you have millions of variables or even billions of variables, then for this kind of model might be your only choice. But if you probably do data reduction, then maybe you can apply some other model, like you said, the random forest. Actually, one of the approaches is you can first apply our method to pre-filter a large portion of the features. Then you apply your favorite models to the reduced data set. This is one way to fit the model. Yeah.
Yeah, it's very interesting you apply the similar methods to both SVM and Lasso. So I'm curious because in SVM we have some different kind of kernel, right? But in Lasso we don't. I'm curious why these two different kind of questions you can apply the same methods.
Actually, their dual problems share some common features.
So your methods also apply to all different kind of kernel.
Yes.
In SVM.
Yes, exactly. Yes, that's a very good question. Yes. But right now, our method we actually didn't consider bias. We just assume the bias is zero. This is a potential way we can improve our method. Yeah.
Another question: have you thought about in Lasso we already have some feature. Have you thought about you invent some new kernel to add in more features so you can screen it?
This is a very good idea, but we haven't tried. Yeah, this I think maybe we can do something like that. Yeah.
Okay, well, it's just on the hour, 1 o'clock. Any further questions or comments? It's wonderful to have you here with us in the department and to have this expertise down that you represent with the E-Lab. It's a big plus for us, and it's going to make a big difference. One thing that we learned the other day from Patrick Harrington, who gave a nice talk, in his experience.
Maybe you were at the data science day.
Something.
Great.
So it was really kind of fun. And Patrick was one of our former students, and he made it crystal clear the importance of these kinds of techniques in the future out into the job market and how we needed this right dead center in our bioinformatics curriculum. I mean, he was very clear about what we had going for us and what we could use to complete ourselves. And there's no question that the expertise that could add to our curriculum that could make us even more cutting edge than we are today is amongst us. We want to do something.
want to make one other announcement. On Monday night, Marcy received a stellar award from the president of the university and the provost for outstanding service and leadership in the librarian function. Jane Blumenthal, not together but separately, also received this award for her separate role.
She's the head of the health sciences library.
And it was really wonderful recognition for you, Marcy, and we're all very proud of you, and everybody should realize how fortunate we are.
I should mention Gil also received.
Oh.
This will never.
Okay.